Okay, we need to finish on Hamming distance or the forward error correction. Just summarise on that really. We've gone through I think 3 or 4 examples yesterday, so you've seen how it works. This is one example of a forward error correction coder where the encoder takes data as input, and in this example it was 2 bits of data and produces a 5-bit code word as output. So that's the encoding process. This is just one example. The number of bits, 2 in, 5 out, may differ, and the mapping from the data to the code words may differ. This is just one example. And what the receiver does is that when the receiver receives a code word, first it checks if it's valid. If the code word is valid, that is, it's one of these 4, then the receiver assumes everything's okay and decodes to get the original data back. Because the transmitter only transmits one of these 4 code words. Therefore, if we receive one of them, we assume there have been no errors across the link and we get the received data. We saw an example yesterday where that's not always perfect. If we transmit the data 0, 1 and there are 3-bit errors, the last 3 bits transmitted are in error. What happens? If we transmit the data 0, 1, we in fact send the code word 0, 0, 1, 1, 1. If across the link the last 3 bits are in error, the receiver would receive 0, 0, 0, 0, 0. The receiver would see that received code word, compare it to the valid ones, think this is correct, and therefore the receiver would have the data 0, 0. That would be a mistake. We don't want that to happen, but it's possible. If we receive a code word which does not match one of the valid ones, then we use the Hamming distance to try and find which valid code word is closest. The Hamming distance is a measure of how close the sequences are. And we choose the valid code word which is closest to the received code word. But it needs to be unique. If there are 2 valid code words with a minimum Hamming distance of the same value, we will not use either of them. We'll just assume that we've detected the error, but we cannot correct. But if there's one received code word with a minimum Hamming distance from our one valid code word with a minimum Hamming distance from our received code word, we will use that. We'll assume that's what was transmitted and we can correct and get the data back. So we saw some examples of how that works. How do we make it better? We've seen examples, I think we've seen an example where we send the data, no errors, it works. We saw an example that if an error occurred, we detected and corrected that. We've seen an example that if an error occurs, we can detect but not correct. And another example, if we have 3-bit errors, that we do not detect the error. The capability of an error correction scheme we measure in terms of how many errors can we detect and correct. We want to minimize the cases that we cannot correct. So how do we make this better? Quiz question. You need to start thinking not just about how the algorithm works, but the principles behind it and strengths and weaknesses. How do we make this approach better? Or this specific example better? Increase the length of the code word. Increase n. Why? No, that would decrease throughput. 0 marks in the quiz. Decrease the chance of error, correct, but why does it decrease the chance of error? Better distinction. That is, the errors or the error correction doesn't work if, as we saw an example, if we have 3-bit errors it will turn the transmitted code word, which is valid, into a received code word, which is also valid. That is, the distance between the two valid ones is some measure of how good we can detect and correct errors. Let's consider another example. First, without increasing the number of bits, let's consider, instead of this table, we had slightly different. The mapping was this. If this was the mapping, our encoder, it's not as good as this one because the valid code words are close to each other. The Hamming distance between them is quite small. If we transmit the data 0, 1, we in fact send this code word. A single bit error, that is, if the last bit is in error, it will turn, so we send it across the link. If the last bit is in error, it becomes this. The receiver sees this, sees it's a valid code word, assumes the data was 0, 0. That's a mistake. That is, the error correction hasn't worked. There was one bit in error. The receiver missed that. That's what we don't want to happen. Why did it happen? Because the valid code words are close to each other. There's only one bit difference between here, and in fact between these two there's only one bit in difference. So this design of the encoder is not as good as in this case because we see the difference between the valid code words is larger, the Hamming distance between them. So the larger the distance between the valid code words, the better the encoder and decoder is at detecting and correcting errors. Because in this case, a single bit error causes a problem. One bit in error causes a problem. In this case, if there's a single bit error in this, we will detect that and correct it. If there are 3 bits in error, we have a problem. So we normally measure the performance of error correcting schemes as how many bits they can detect and correct. And that's related to the distance between each of the valid code words, the Hamming distance in this case. The more different they are, that is, if we can distinguish between the valid code words, then it makes it easier to detect and correct. And yep.
If we have less n, it's not good.
So coming back to the answer, if we make n larger, we can have more distinct valid code words. If n was 10 bits, then with 10 bits, we have 1,024 possible code words. We only need to choose 4 of them as valid, so we can choose 4 that are very different from each other. I don't know what's the best one. How many bits? Just as these two examples, there's a large distance between these two. Therefore, a single bit error, if this is transmitted, will not turn the received code word into this. A 3-bit error in this will not turn the received code word into this, and therefore we should be able to detect and possibly correct the error. That is, with larger n, we can distinguish between the valid code words easier, and that means we can detect and correct more errors. So, in fact, there's 2 parts that come up here. The selection of the actual code words is important in the design, and to make it easier to select distinct code words or different code words, increasing the length of the code word allows us to do that. A larger n allows us to have better error detection and correction capability. And the problem with a larger n, what's the problem with a larger n? Increase the overhead. Decrease throughput. Good. When I say larger n, I mean relative to the length of the data. If we have 2 bits of data, in this case we send 5 bits of code word. If I make a 10-bit code word, for every 2 bits of data I want to send, I now have to send double amount across my network, 10 bits of code word. So we're effectively, for 2 bits of data, we're sending, in this case, 5. We have 3 bits of overhead. If we had 10 bits here, it'd be 2 bits and 10, there'll be 8 bits of overhead. So increasing n decreases the efficiency or throughput, but it increases the ability to detect and correct errors. And in fact, that's what the last slide of our lecture says. And that applies to both error correction and error detection. If we have k bits of useful data, n bits transmitted, then we have some efficiency of k over n. Keeping k constant, make n larger, detect and correct more errors, which is a good thing. But if you make n larger, you lower the efficiency, which is a bad thing. That's the trade-off that we need to deal with error correction and error detection. Any questions on our last topic?
Yes.
No, that's after the midterm.
After midterm, yay!
Yeah, this is our last topic. It doesn't mean the lecture's finished. Any questions on error detection and error correction? We have 2 more things to do, talk about the midterm and then give some examples from the midterm. But before we do that, let's finish on this topic. Everyone could answer a surprise quiz. A surprise quiz now about error correction.
Do you have practice exam for us?
Let's talk about the midterm exam.
You have answer for this in web.
Yep.
Yes. Okay.
Hang on, here's the midterm for this year. So just the front page. "17 pages is the length of the exam. It's closed book, no dictionary, calculator is allowed and encouraged. I think you'll need it. If you don't have a calculator or if you forget it, then do the questions and try and solve it to as much detail as possible. Most questions you can do it in your head, but I think some, if you want to give that correct answer, you'll need a calculator. Normal things. When we talk about a sequence of bits, I assume the first bit is the leftmost bit and the last bit is the rightmost bit. So if I say, here's a sequence and the 4th bit is in error, then you know it's this bit 0 is in error. That's the 4th bit in the sequence. Speed of transmission, the speed of light, 3 by 10 to the 8 meters per second. Free space is given the area of an antenna, or the antenna gain, depending upon the area of the antenna, is given. Of course, be careful with this. The effective area is not necessarily the physical area. If we have a dish or a parabolic antenna, let's say the physical area is determined by the radius. If we treat it just as a flat circle, then the physical area of this antenna is pi r squared. You can calculate that. But the effective area is not necessarily equal to pi r squared. It's a ratio or a factor, and that ratio I would normally give you. That is, I would say, here's an antenna with 1 meter diameter. The effective area is 1/2 of the physical area. Then you would know, okay, diameter is 1 meter, radius is 1/2 meter, pi r squared gives us the physical area. The effective area is 1/2 of that. And then you can use this equation. So they are given. There are 8 questions. 8 questions. 3 hours, everything up until today and including today. Digital data communication techniques is included. All right, you can use previous year's exams to study. There is answers and questions on the website and quizzes. Those two equations were given. The other thing that you don't have to remember, you need to know non-return to zero level and non-return to zero invert on ones. They're the two simplest ones. The others, Manchester, bipolar, AMI, you don't need to remember how they work. But if I gave you a description, Manchester encoding is when you have a bit 0, you have high to low, and when you have a bit 1, you have low to high. If I gave you a written description, you could answer some question about it, but you don't need to remember what Manchester encoding is. You need to remember these two, or you may need to. Of the 8 questions, the first question is, all questions have multiple parts. The first question is, fill in the blank space. So it's some statement, and there's a blank space. You need to put the right word or phrase or acronym in that space. And you get to select from, I think it's about 50 words. That is, I give you the words to select the answer from. 50. So, not 500. I don't know, it's not 50, it's slightly less, I think. But there's a table of words, or phrases, or acronyms, and there's a number of parts in this question, and with blank space you need to select the most appropriate one and put it in there. The remaining 7 questions are calculation questions, asking about concepts and so on. And that's all I can think of about the midterm. Any questions about the structure of the midterm? How many percentage for the total score? Can anyone remember? I think it's 30%. I think so. So, what do we say? The assignment 15, quizzes 20, that's 35. 30 for the midterm, that's 65, and 35 for the final. Assignment will come after the midterm. Any other questions about the midterm exam? You only have a few days remaining, I think, before the exam, so you've already started studying. Okay? No, you still can make it up on the midterm. So use the past exams. Use past exams. Sometimes the questions change, sometimes they don't. Or sometimes they're similar to the past exam, sometimes there's a few questions which are completely different. But covering the same concepts that we've seen in quizzes, in examples, and you'll see in past exams. What's the time? 20 minutes left. We'll just use that. Unless you have specific questions, I'll use that to go through last year's exams. Any questions on particular topics that you want me to address in the last 20 minutes? Let's look at last year's exam, which you have in the handout. We won't answer all of them. We'll just give you an idea of the types of questions. Okay, draw the 5-layer stack, or the TCP/IP stack. You need to know those 5 layers. Some relationship between the layer and an address. An IP address, which layer? Network layer. So this is going back to the start of the semester. A hardware address. Data link. Data link, physical would also be acceptable because sometimes we call them a physical address. So this one. My email address. Application, okay. Web server port. Transport layer, port numbers are part of. What's a port number do? What's it identify?
Identify application trace.
Yeah, that identifies the application process running. So I have multiple processes or applications running on my computer. The port number is used to identify that. We've answered that while you were talking. We said it's a part of the network layer.
Yeah.
So it's network address, data link, transport.
Network, application, data link, transport. The answers are on the website. You'll find them. Very quickly on this one, we have a signal. How many components in this signal? How many components? 4. Frequency of the first component? How many megahertz? 10 megahertz. So for this, you need to remember, or it's useful to remember the general equation for our signal, that peak amplitude sine 2 pi times by the frequency t plus phase. So that's the general equation, and then to determine the frequencies of the components, we can just equate it to this, find out what f is. 2 pi ft, we have 2 by 10 to the 7 pi t, therefore f must be 10 to the power of 7. 10 to the power of 7 is 10 megahertz. So the frequency of the first component is 10 megahertz. The second one, the third component, the first component had a frequency of 10 megahertz. The second component is sine 6 by 10 to the 7 pi t. So f is 3 by 10 to the 7, which is 30 by 10 to the 6, which is 30 megahertz. Third component, 50 and 70, the last component. And the plot of this signal in the frequency domain is simply impulses at each of those component frequencies with amplitude equal to the peak amplitude given in the equation, the value of A. First component, 3. Second component is 1, and then the other 2. So that's our plot given in the frequency domain of that signal. Fundamental...
We have not to scale it exactly.
No, you would not have to scale that exactly. It would be useful to identify what these points are, whatever it is, 0.6. But you don't have to use a ruler even. You can just draw that quickly. Doesn't have to be to scale perfectly. This one, of course, should be much smaller than this one. If you drew this and said this was 0.6 and this was 3, I would not give you full marks.
Can we put it on the top of circle?
You can put here 3. If you point 1 here, again. So it's about giving a general idea. It doesn't have to be perfect scale, but it needs to show one is larger than another. What's the fundamental frequency of our signal? The fundamental frequency is in general, if all of the component frequencies are integer multiples of one of them, then that one is the fundamental frequency. They are all integer multiples of 10 megahertz. Therefore, 10 megahertz is the fundamental frequency. 10 megahertz is the frequency of our signal. And the period is the inverse of the frequency. 1 divided by 10 million is the period then. 1 over 10 million is how many microseconds? 0.1. This question is similar to your quiz question. We won't go through it, but what it does is it, instead of using the free space path loss, it introduces a different path loss model. So I give you what it is, and we see that equation at the top that relates the factors. It doesn't matter what path loss model being used, that equation at the top is always the same. A path loss model determines how do we calculate L. In this question, the way to calculate L, the loss, was given here. And it's measured in decibels. So it set up the question, and then it was just a simple calculation of, I think the questions were, right, what's the transmit power? So we're not going to read through the question, but it will give you the idea of what's being asked. What is the transmit power measured in dBm? So if you know the transmit power measured in milliwatts, you need to be able to convert to dBm. If you know the transmit power measured in watts, you need to be able to convert to dBm. Wavelength of the signal, so you need to know that the wavelength lambda is C divided by F. And then in this case, okay, if we have some distance, then there were 3 antennas to choose from, which one was best. So again, using this equation for calculating, if we transmit with this power, we have 2 antennas which introduce some gain, and we need to receive with some power, and we know the loss, then in this question you need to find out which antenna will allow us to cover a distance of 20 meters. You need to read through that to fully understand. We don't have time for that one. PCM, here's an analog input signal, 10 kilohertz, 3-bit PCM. So it tells us that we sample 10,000 times per second, and each sample is 3 bits in length. That is, we choose a number between 0 and 7. So this gives us the scale of time. So with 10 kilohertz, when are we going to sample? Let's say we sample at the first point. When's the next sample? 3.2. Why?
10 kilobit พีเรียดมัน
Yeah, so we have 10,000 samples per second. 1 divided by 10,000 is 0.1 milliseconds. One sample period is 0.1 milliseconds. Our scale is milliseconds. If we sample at 3.1, the next sample at 3.2, then at 3.3. So be careful. Another question may say, okay, the sampling rate was 20 kilohertz. Therefore, we'd be sampling here, here, here. A higher double the sampling rate would halve the sample period. So you need to know those values. All right, and then you need to take those samples and work out what the digital values were. And in this question, once you got the sampled values, it says that we get the digital data and then we send that as a digital signal using non-return to zero invert on ones. So you have the input bits and then you need to use non-return to zero invert on ones. And that is when we have a bit 1 to transmit, we change the level. When we have a bit 0 to transmit, we keep the level the same. Invert on bit 1. So you had to know about PCM to get the digital data, the sequence of zeros and ones, by sampling this. And then from that sequence of bits, draw the transmitted signal. Again, we don't have time to explain this one, but just to give you a taste, so you'll study. This is a description of an alternative modulation technique, delta modulation. So instead of using PCM, what if we use this other one? So it describes how it works. So you don't need to know beforehand how it works. So if I described a different technique in this year's exam, then you would read, understand that description, and then try and answer the questions based upon that. Delta modulation. We sample such that we produce this what's called staircase output. It's always at each sample point, it's either going up or going down. It gives a description of how do we calculate the next value. Basically, if we have at this point, if at the next sampling point, if the signal level is above the current level, we'll go up. And the next sample point, this point is above us, so we go up. And if at this point the input is below the current level, so we go down. So we're trying to follow the input analog and produce an output digital signal, or output digital data. But that's all described there. And then from that, work out or answer some questions. This question is about what? Delay, I think. Here's a network scenario. We have a set of links. So one link from a computer to a gateway, a link up to a satellite, a link down. So treat all the links separately. The link characteristics are given, the distance and the data rate. So in terms of calculating delay, you can find the propagation delay of each link. So you need to know the propagation delay is the distance divided by the speed of light. And the transmission delay for each link, which is the size of the data divided by the data rate. The size of the data is given somewhere in the question. And the total delay from A through to B is the sum of the delays across each link, plus the delays inside the nodes. So you need to know those 4 delays. What are they? The 4 components of delay.
Propagation delay and queuing delay.
Yes, so one way to think about them is that the propagation delay and transmission delay are related to links. So each link has some propagation delay, depending upon the length of that link, and has some transmission delay depending upon the data rate of that link. In addition, each node has some processing delay and some queuing delay as well. So you can think of processing and queuing at the nodes, transmission and propagation at the links. Total delay is the sum of all of them. It's just additive. If you remember that, I think you can answer any question in this form. Be careful if the question is asking about what's the response time, then it's the time to send a request and get something back. You need to consider both directions. And that's what this question asked. Propagation, transmission, what's the total delay? This question is a simple one about, initially simple about, we have some encoding format. What's the size of the data produced? And that's similar to the question we had in the second quiz, in this quiz, in the second question. That is, in this case, we're talking about video, where video is a set of frames which are changed over time. So what all video is still images where they are rapidly changing to represent motion. So each image in this example is a particular size, 1920 by 1080 pixels. Each pixel or dot is represented or represents a color, and that color is a 24-bit number. So we have on every image this many pixels, which whatever it is, almost 2 million pixels, and every pixel is 24 bits. So we know the number of bits in every image. And a frame rate says that we have 25 frames per second, 25 hertz. It's 25 per second. So in 1 second, the number of bits we have in this video is 25 frames per second, 25 times by the number of pixels, 1920 by 1080, times by the number of bits per pixel. Multiply those 4 numbers together and you get the number of bits per second. And then you can answer some questions about that. Similar with that we saw when we encoded audio. With PCM we had a sampling rate, the number of samples per second, the number of bits per sample. We can work out the size of the file produced. Then it says, okay, what if we compress all of this? In reality, we don't send raw video, we compress it. So if our raw video was 100 megabits, and we could compress it to be 1% of its original size, then the compressed size would be what? Raw video 100 megabits, compressed size would be what? 1 megabit, 1% of the original size. So let's say it starts out as 100 megabits. In this example, it compresses down to just 1 megabit. And then you could answer questions based on that. What equation are you going to remember and use in this question, in part A? Nyquist. As soon as you see noise-free, you recognize, okay, this is probably going to be about Nyquist capacity. And the second part? Okay, because it's related, we're talking about noise, we're talking about signal strength, so something about signal-to-noise ratio. We know the bandwidth. What's the data rate or capacity? Shannon capacity. So you need to remember those 2 equations, Shannon and Nyquist. Okay, here's an example of the fill-in-the-blank type questions. Set of words, fill in the blanks in those statements. See if you can do it. Part A. Hamming distance is the best answer there.
No penalty.
No penalty for wrong answers.
Yeah, okay.
0 for a wrong answer, 0 for no answer.
Yeah.
Full marks for right answer. And only 1 answer. 2 answers, and unless they're both correct, if you give 2 answers, say you put in 2 different things here, if one of them was wrong, you get 0 marks. So don't try and just put everything in here and hope that I'll give you the marks. I think you can do that in your own time, just with 2 minutes, see what's left. This one's not covered. We haven't covered this topic yet. That's the next topic after the midterm. We haven't covered flow control or error control yet. We've covered parts of this, but not all of it. That is, we've skipped over one thing. You could answer some parts of this, but the things about jitter you could not answer. We did not cover that. Here's the set of packets, so the details of the packets, the time it was received, the time it was sent, the size of the packet. First question, what is the average delay? Okay, so you have 6 packets, you need to work out the delay of each packet. The delay of the first packet is what? So, yeah, so the timestamp tells us at what time was it sent. So the sender puts some value in it We're sending at time 0. We receive at time 7, therefore the delay is 7 milliseconds. Next one is 8 milliseconds, from 3 to 11. Get the 6 values, take the average, and you have the answer. The average delay in that case. Jitter we have not covered. Throughput is, remember, the rate at which we receive the real data. So how fast, how many bits or bytes per second are we receiving? One way to calculate it in this one is that we've transmitted this total amount of bytes over some period of time. So the receiver between time 7 and time 23 over 16 milliseconds has received the sum of these in bytes, which is whatever, 600, 700, 720 bytes received in 16 milliseconds. 16. Start at 7. The first one we receive is at 7. The last one at 23. Therefore, over that period of 16 milliseconds, we receive 720 bytes. 720 bytes per 16 milliseconds. 720 bytes divided by 16 milliseconds gives us the rate at which we've received data, a throughput. And the last question is, I think, coming back to one of our first or second lectures, what happens when we introduce headers? We have some overhead, and being able to calculate that's important. Jitter we did not cover. And that's the end of this exam and the end of our lectures. Your life will continue after the midterm. Sorry? Yes, no overhead. So, study for the exam. Ask me questions over the next few days if you have any. Otherwise, I'll see you at the exam. Good luck.